Hello, my good students. I trust you are well this morning, and I want to welcome to our today's session. We are going to cover isomerism as our topic. So, as a student, when you hear isomerism, what comes in your mind? Here, there are two vocabularies. One of them, so there are two vocabularies here. We have the itself, the isomerism, then we have the isomers. So, we need to ask ourselves, what is this we are calling isomerism? And isomerism is the existence of compounds that have same molecular formula but different structural formula. So they share same molecular formula, but you're going to see they have different structural formula. And that defines isomerism. So all these compounds that are going to exhibit these properties are what we now call as isomers. So there are two terms. So isomerism is what we can say is the existence of the compounds with same molecular formula but different structural formula. For isomers, these are now those compounds that we see have those properties. So my focus this morning will be on isomerism in alkanes. And you know, when it comes to alkanes are those compounds that we can say are saturated. So they are saturated organic compounds. The question now will be, what do we mean when talk about some compound being saturated? So in chemistry, we say that if an organic compound lacks the double or the triple covalent bond, then we say it is saturated. And you know that when it comes to alkanes, they have a general molecular formula which you can represent as CnH2n plus 2, where we all know that n is equal to the number. So n is going to represent the number of carbon atoms. So n represents the number of carbon atoms. So I'm going to start off by looking at pentane. So pentane is the fifth member of the alkane series. So we can therefore be able to substitute in our general formula where n is equal to 5, so that we are going to get pentane as C5, then H, we're going to have 10 plus 2, that is 12. So we want to look at what are some of the isomers in pentane, the compounds that are going to have this same molecular formula but their structures are going to be different. So we can start off by, first of all, showing the structure of the pentane. So it has 5 carbon atoms that are joined together in a continuous chain. Then we can be able to attach our hydrogens. So that is our first isomer. As we can be able to see, we can establish how many carbon atoms are there. So we have 1, we have 2, 3, 4, 5. We can even count how many hydrogen atoms are there. And if you are able to determine, there are 5. So we are going to give this the name. Remember, when you're naming, we have to establish the longest continuous chain because that becomes the parent name. In our case, there are 5 carbon atoms, meaning our parent name becomes pentane. So our name for the compound, we shall call it pentane, and that is our first isomer. So we can go ahead and ask ourselves, so how do we come up with isomers? So what we do is simply rearranging the carbon and the hydrogen atoms. So we just uh, reduce the number of carbon atoms in the longest continuous chain. Like in this case, I can decide in my second one, I can decide it to have 4 carbon atoms. And remember, from the chemistry, you'll be able to learn one carbon should be able to form 4 covalent bonds. And when forming isomers, I always encourage my students, they should not attach any of the carbon atoms on the either the first on the left hand side or the first carbon from the right hand side. So you are free. Like in this case, I may decide, let me pick this whole molecule from our pentane. Then I'm going to attach it on any given carbon. Maybe I can decide, let me attach it here. And it has 3 carbon atoms. So I'm going to attach it as a CH3. Then we can be able to fill the remaining hydrogen atoms. So we need to establish how many carbon atoms are there in total. So again, we can go ahead and even count. So we have 1, 2, 3, 4, 5. So it meets the number of carbon atoms in our formula. We can also go ahead and establish how many hydrogen atoms are there. So again, we are going to see we have 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. So it satisfies that it has same molecular formula. However, the structure is different, and that is now where we are referring to the issue of the isomers. So these two are what we can call isomers. They have the same number of carbon atoms, same number of hydrogen atoms, but they only differ in terms of the structure. So we can be able to give the name. So there are rules that are supposed to be used when naming organic compounds. Rule number one, it is to establish the longest continuous chain. In our case, it has 4 carbon atoms. So there are 4 carbon atoms. So that means we expect our parent name to be a butane. But it has something else which we have been able to bring, which I have circled with yellow, what we now call our substituent group. It becomes a substituent group. So we need to establish what is the name of this substituent group. And from the look of things, is the CH3, then that makes it to be a methyl. So we need to go ahead and assign its position. And assigning position, we must be able to establish what is the lowest position of our substituent group from either side on the longest continuous carbon chain. And we can be able to see that from our right hand side, it is attached to this carbon. And what is the position of this carbon? Carbon number 1, carbon number 2. That is from my right hand side. From our left hand side, it is carbon number 1, carbon number 2, carbon number 3. So we have 2 and 3. So the question is, which is the lowest? And in this case, 2 is lower. So because we must give the position. So we are saying this position from left hand side, it's on carbon number 3. But from our right hand side, carbon number 2. So this becomes the lowest position. So with that, we can now go ahead and give the name of our compound. So we start by showing the position on which our substituent group is attached. In our case, it's on carbon number 2. And we shall have a hyphen. What is the name of our substituent group? It is a methyl. Is there any other? No. So what is the parent name? It was a butane. So that means the correct name of our isomer becomes 2-methyl butane. And that is the second isomer of pentane. We can go ahead and also ask ourselves, from this, is it possible to get a third member? Yes, it is possible. Again, we can shorten the longest continuous chain. So we can pick one of the carbon with hydrogen and attach it on the carbon at the center. We can still do the same, the other ones. Then we can now distribute the hydrogen on the outer carbon atoms. Again, we can want to establish, are there 5 carbon atoms in total? So we can be able to see there are 3, 4, 5. In terms of hydrogen atoms, again, we have 3, we have 9, we have 12. So it satisfies the condition of having the same molecular formula. So you want to go ahead and name this compound. So remember, as I said, when you are forming isomers, we should always try as much as possible not to attach any of our substituent groups either on the first carbon from the left-hand side or the carbon from the right-hand side. So with that in mind, we can just play with these carbon atoms and hydrogen atoms in between. So we can go ahead and give it a name. So we can be able to see it has two substituent groups. So we have a substituent group. We also have a substituent group there. Then both of them are attached to this carbon. So we need to establish the lowest position from either side. We can see from right hand side, carbon number 1, carbon number 2. From left hand side, carbon number 1, carbon number 2. So it means the lowest is carbon number 2. Then our substituent groups, there are two methyls. So with that, we can go ahead and give a name. And of course, we have our parent name. So I forgot to mention that. So in this case, our parent name has 3 carbons. That makes it to be a propane. So we can go ahead and now name our compound. And because these ones are true, the substituent groups are true, and they are the same, then you are going to use some prefixes. And in this case, we use di in case they are two. If they were 3, then we shall have used tri for 3. In case they are 4 and they are similar, we should have used the prefix tetra, meaning they are 4. But in our case, they are only 2. And so we give the name, just like the first one. We shall start with the position of the substituent group. So the first one is number 1. It's on carbon number 2. Then we put a comma. We have the second substituent group. It's also located on carbon number 2. So we have been able to indicate their positions. Then we use a hyphen. What is the name of our substituent group? It's a methyl. But how many are they? There are 2. So which prefix do we use? Di. So we shall say dimethyl. Then we go and ask ourselves, what is the parent name? In this case, propane. And that becomes our third isomer. So in other words, we can conclude that pentane. So pentane has 3. So in our case, we can conclude that pentane has 3 branching isomers, which you have been able to see. So the first one being pentane, the second one, what we saw as 2-methylbutane, and the third one is what we are calling 2,2-dimethylpropane. So that is how we can be able to show isomerism in pentane. So we can be able to see that in all the 3 compounds that have been formed, all of them, they have the same molecular formula where there are 5 carbons and there are 12 hydrogens. Where they are differing is in terms of their structure. If you look at the structure of pentane, it's different from the structure of 2-methyl butane as well as the 2,2-dimethyl propane. So that is the easiest way in which we can be able to draw to show isomerism in an alkane. So we can be able to apply this knowledge to undertake or rather show isomerism in hexane, in heptane, whichever alkane molecule that you can think of. So thank you so much for following up our lesson today. I look forward to seeing you in our next session. Thank you so much.